All right, it says a couple is applied to a tap as shown. All right, so you've got the distance to the pivot to a force, but it says what is the torque of the couple? So we have some anti-parallel forces that are the same magnitude. That sounds like a couple to me. And remember that the definition of the torque of a couple is one of the forces times the perpendicular distance between them. The perpendicular distance between them would be 2d, and one of the forces is F. And so we're looking for F times 2d or 2FD. Just knowing the definition of torque is enough to quickly get you to see. You don't have to second guess yourself. That's a really straightforward one, and you move on. Okay. The entire distance between them is 2d times one of the forces F. And so it's this. The other way to consider it is I've just got my moment of force times distance, but I got two of them. So if you said I've got my moment of force times distance, but I got two of them, you get the same answer. Moment of force and torque of a couple are really the same thing. Okay, they're really kind of talking about the same thing. We just need to sort of consider it the way that it's defined there. Okay, where the torque of a couple produces that turning effect, there's no resultant force. So the torque of a couple, that's when we have two anti-parallel forces that are of the same magnitude acting, some perpendicular distance away from the pivot. That distance times one of the forces is the torque of a couple. Now this one here looks a little bit trickier. It says a crane uses a counterweight to stop it from toppling over when lifting a load, as shown. The counterweight has a mass of 5,000 kilograms. The crane is required to lift a load of 12 kilonewtons, and the horizontal distance from the pivot to the load is 17 meters. How far from the pivot should the center of gravity of the counterweight be positioned in order to keep the crane in equilibrium, or equilibrium if you prefer? So it's either going to be 40 meters away, 4.16 meters away, 0.24 meters away, or 0.0408 meters away. I think the easiest thing to do here is let's convert that counterweight into, that mass that's given into a weight. How do we do that? $5,000 times 9.81, right? Mass times G is weight. And so that's 49,000 pounds, 49,000 newtons rather, pounds. So what's that? If we got 12,000 newtons over there, but we got 49,000 newtons over on, this side over here, right? This is 49,000 newtons. This is 12,000 newtons. This one weighs more. Does it weigh so much more that we only have to put it 4 centimeters away from the pivot, or like 24 centimeters away, or 4 meters away? Remember, this one is 17 meters away. This is a crane. Okay, it's a big piece of heavy machinery. My intuition tells me probably the same thing yours does. What do you think is the right answer here? No calculation needed. I mean, I know we calculated this, but what do you think it should be? It's probably C. I think C seems reasonable. I think this is way too big, right? We're going to put this thing 40 meters away. That will cause it to topple over the other way. Like, we need this weight here because if all we do is lift up 12,000 newtons of weight, the crane has so much torque on this side that it falls over. So we need a counterweight. And so we use the principle of moments to say, okay, well, this one is producing a moment that's going this way, clockwise. This one is producing a moment that goes this way, anti-clockwise, right? Even though they're both weights that act straight down, because they're on opposite sides of the pivot, they're producing different moments, right? This one is a clockwise moment. This one is an anti-clockwise moment. The pivot is here, right? The hands of the clock, clockwise, anti-clockwise. So the formal way to approach the calculation is to say we have a clockwise moment equal to 12 kilonewtons. So remember yesterday, knowing that kilo means 10 to the 3, make short work of the conversions. times 17 meters. Never convert a Newton meter of moment into a joule, okay? A Newton meter stays a Newton meter when we're talking about moment of force. 12,000 times 17 is 204,000 Newton meters. Equilibrium means no net moment. Okay, to keep this in equilibrium, we're going to need the same amount of anti-clockwise moment on this side. And so what we've calculated here is that they've given us a mass, okay, and we need to calculate its weight to know what is the force due to gravity is mass times g. And so that was the sort of calculation we began with. 5,000 times 9.81, remember, was 49,050. So the weight of this one is 49,050 newtons. And we're solving for how far away, we'll call it R, how far away do we need to put that counterweight? Like we can sort of move this because we might be lifting different weights over here, right? And so this can be adjusted based on how much weight we're lifting over here. Okay, so we have a fixed sort of counterweight, but what we can move is R, because remember the equation is force times distance to the pivot. So it's like we could either, you know, like because this is the variable thing on this side, we adjust this with a fixed weight on this side, right? To just keep sort of the moments equal no matter what. Sometimes we might lift a 12,000 Newton, you know, weight. Other times it might be 15,000. We're gonna have to move this thing further out, okay, to keep it balanced, all right? Or if it's less weight, we have to bring it closer in, okay? So R is adjustable sort of for this. How far do we move it? You're the mathematician that's working for this engineering company to say, hey, this morning we're lifting the 12,000, you know, Newton truss here to build this building. How far do we need to move the counterweight so that, you know, we don't all die? And I go, hold on, let me just calculate. That's the old principle of moments there. Hopefully my high school physics serves me well here because lives depend on it. 49,050 times what R makes it equal to this principle of moments. These are my anti-clockwise. These are my clockwise that way, anti-clockwise that way. So we're dividing each side by this. If we left it as 5,000, maybe we get an answer of 40.8. No, that would be 204,000 divided by 5,000 is sure enough 40.8. Okay, students that don't have the distinction in mind between mass and weight will go, oh, 5,000, that's the weight here, right? And they'll get this wildly incorrect answer. We can't put it 40 meters away. That will topple it the other way, all right? And so you must convert, you know, the mass given into weight to get 204,000 divided by 49,050. And then we know that R equals 4.159. That's not one of the answers given, so we must have done it wrong. Happened again. Okay, 4.16. That's about 4.159. All right, we won't let that bother us. We're good. Don't worry about it so much when you don't see your exact answer there, okay? 4.16, once we deal with the significant digits, that's the right answer.